Hello and welcome to another Stephen Mendes video. In this video we're going to show you how computers do division. Some knowledge of computer operations is assumed, but you should find it pretty easy to understand the content. Here we are considering the business of dividing 203 by 13. Most people have learnt this already when they were children in school. We say 13 into 2 cannot go. Then we say 13 into 20 goes one time, and we write the 13 down under the 20 and subtract it. We get 7 as a remainder of that operation. Then we bring down the next digit to the right, which is 3. And we see that the 13 goes into the 73 5 times, which gives us a result of 8. We've now reached the end of the digits of which we're trying to do the subtraction. There are no more on the right-hand side to bring down. So our quotient is 15. And our remainder is 8. And that gives you some idea there of how we do division. Let's convert it to binary and see how it works in binary. So there we have the same 203 with 13 over on the right hand side being the divisor. And we use the same process. We can't put that divisor into 1, and we can't put it into 1, 1. As a matter of fact, we have to go all the way over to the 5th position before we have a number big enough to take 13 from. So we write the 13 underneath and we subtract it as expected. Now we're left with a remainder which is not big enough, of course, to take another 13 from. Here is the difference now. We can only ever have 0 or 1. We can't have several other multiplications like we had 5 in the other one. We either can take away the 13 or we can't take away the 13. Bear that in mind. So it's either a go or no go, 0 or 1 situation. We bring down another 0, and once again we go. We can take away 13, so we put a 1 above. And we end up with some remainder which is smaller than 13. So we bring down another digit, and once again we can subtract. So we get another 1 up top, and we're left with another remainder. We bring down the final 1. We do the final subtraction, and we are left with a quotient of 15 and a remainder of 8 in binary. Now let's begin to analyze what we're actually doing. We have brought down some numbers from above to the right. To the end, we bring down 1 at a time, as you can see with the green arrows. The other thing that we are doing is we are actually shifting the 13 to the right. And you can see that here. It's the same 13, but when we first subtract it, we have 1 0 in front. And as we continue to subtract it in every row, we add an additional 0. So our 13 is moving to the right relative to the dividend. There it's moving to the right. So we have to right shift the divisor to subtract it from the remainder combined with another bit from the dividend. So make sure you understand what's happening here, and then we can continue to go the computer algorithm. One thing that you have to notice is the rule about the quotient at the top. We put a 1 in the quotient if we can subtract, and if we put a 0 into the quotient if we cannot subtract. We're going to follow the division process through a typical microprocessor. We are going to use the Intel 8085, which is an extremely popular processor. And we only need the A register or accumulator, the B register, the C register, and the HL register pair. Don't be too disturbed if you don't know what that means. A register is just something that holds our ones and zeros and allows us to manipulate them. The routine that we're going to execute is called an unsigned single precision divide subroutine. Simply means that the numbers that we're trying to divide are all positive. Unsigned means they're positive, and it's a single precision divide because the divisor is only 1 byte in length. The first thing we do is to clear the A register for the remainder. We are going to perform an XOR. If we XOR a register with itself, it zeros the contents so that the A register will contain all zeros. That's just the purpose of that. And the remainder, whatever remains when we're done, will be in the A register. The next thing we're going to do is to set up a loop counter so that we will know how many times we have to go through this code. There is no need to go through this code for more than the number of bits, and we have to know when we reach the end. Remember, when we were doing the division on paper, we reached the end when we had performed with the last digit, and there were no more. So whatever was left back had to be the remainder because there were no more digits. So we know that we've gone through all of them when this counter runs out. Then we proceed to the start. That just means we're jumping to the start of the routine. We have a label called start, and we move from that point in the code to the point that has a label of start on it. Now this little piece of code is what actually does the subtraction. The first line, sub B, says that we're going to subtract whatever is in B. We are going to put our divisor in B before we start the routine. So we will subtract the divisor from essentially the remainder. But the remainder has to grow to be big enough for us to take the divisor from it. And if we take it away before it's big enough, we're going to get a negative result, which will let us know that A is not yet big enough to take B from. So we will have to add it back. So the add B just puts it back to how it was before. So essentially what this little three line of code is doing, it's testing to see if we can in fact subtract B from A or not. The shifting that we're going to do is we are going to shift our dividend bit by bit into what will ultimately become our remainder. That these two lines of code have the same effect as the pulling down of the ones so that we may carry on. We are going to shift it a bit at a time into that, and then we'll take it away from the A register. So we shift the dividend bit by bit into the A register through the carry bit. Okay, now these three lines of code look very similar to the two above. We have another shift left and a rotate of the A, but this time we've added an increment instruction. So we're going to increment the HL register pair because at this point, if this no restore piece of routine is executed, it means that we were successfully able to subtract B from A. So we need to put a 1 in the quotient. So basically the quotient comes into the right side of the HL register pair as the dividend moves out of the left end of it. So we start with the dividend in HL and we end up with the quotient after all the bits have been shifted out. Finally, we continue to loop the count until we've processed the entire dividend. So this just subtracts the counter and tests to make sure that we have not reached 0 in the C register, which is serving as our counter register. And once we have processed the whole lot, we need to compensate by right shifting the remainder 1 bit position. So this is just a tidy up procedure. Restoring the remainder in A just compensates and moves it 1 position to the right, because at the point that we came out of the loop, the order of operations, we had already done a shift. So we have to compensate for that shift and just push it back 1 position. So now you've seen the entire routine. We're just going to give you a little more detail before we start. Okay, now we're just going to explain those critical instructions that are going to play a part. The DAD-H that you see in the code adds the HL register basically to itself. And when you add an HL register to itself, it's the same as shifting it 1 position to the left. And what comes out of the leftmost side will go into the carry bit. So we are shifting the HL register's leftmost bit into the carry with this instruction as well. The sub B subtracts the register B from the register A and sets the carry flag if the B is greater than the A. So that carry flag, which is actually working as a borrow flag in this case, but it's called a carry flag, whether it's borrow or carry, just depends on what operation we're doing. That's going to allow us to determine whether B is greater than A or A is greater than B. And we need to know that because we let the subtraction stand if it's valid. If the B is less than the A, we let the subtraction stand. But if the B is more than the A, we need to restore the A register to what it was before, as I indicated when I gave you the code. Now, the final thing that you need to understand is this Ral instruction. This Ral instruction simply shifts the register A to the left through the carry bit. So it's sort of a 9-bit rotate. As you can see there from the diagram, what comes out of the most significant bit goes into the carry, and what was previously in the carry goes into the least significant bit. Initially, when we start, only our dividend is in the L register because our number is not big enough to go into the H register. We selected a number of 203, which holds well within 1 byte. So that's why you see that we've zeroed the A register and the dividend is in the L register at the top. Now, we're not going to show all the individual shifts because after each shift, the dividend will shift. But after 9 shifts, in the next diagram you see below, after 9 shifts, the dividend has moved into the H register or high order register, and 1 bit has come out into the carry. And after 10 shifts, another bit has come out of the H register and gone into the carry, and what was in the carry before has gone into the A register, which is at the bottom. So the H is on the left at the top, the L is on the right, the carry is next underneath, and then at the bottom is the A. So the 1 has gone into the A register after 10 shifts, and the 1 has come out of the HL and gone into the carry. Now, after 14 shifts, enough of the dividend has been transferred through the carry into the A register to permit a subtraction. You see, I put a little red there to let you know enough has been transferred into the A register to subtract the divisor. So we do that in the next bit. We subtract the divisor and we're left with what remains in the A register. And we now have to shift some more bits because the right end of our dividend is still in the H register. So once again, using the carry bit, we shift out another bit. And after shifting out another bit, we have to increment the HL register for the last subtraction that we did. As you can see, I've put a red sign there to let you know that we have incremented. That means we've added 1 to the register. So this is how the quotient comes in on the right side of HL as the dividend comes out on the left side. But we've shifted one more bit and our remainder, or whatever is going to become our remainder, is now big enough to do another subtraction. So we subtract the divisor again, which, as you can see, lowers the value in the A register by the amount that we have subtracted. Then we do another shift, and after we've done the shift, we increment the HL register pair. Now, the shift and the increment are shown on the same diagram, but you should realize that shifting will create a 0 on the rightmost bit, which, when we increment, will become a 1. So the 1 that was there on the rightmost bit of the L register moved to the left, and a 0 was created, which has now been filled by our incrementing for the last subtraction. Remember, every time we subtract, we must increment. If we don't subtract, we don't increment, which leaves the 0 there, and the 0 gradually moves across in the quotient. Anyhow, looking on the left side, we see that we now have enough bits to be able to perform our subtraction again. So on the right side, we see divisor subtracted, and the value in our A register has been reduced by that amount. We now do another shift, which moves our 1, 1 to 1, 1, 0, and then we do another increment for the subtraction that we just finished accomplishing. And when we do that, we have enough now in our A register to do yet another subtraction. So on the bottom right hand side, we do a subtraction, and after we've subtracted, what's left in the A register is smaller than the divisor, so we need to do another shift. This shift is going to be our last shift because it brings the last bit out of our carry into our remainder, which is actually where the subtractions are occurring. So if you look at the value there, you'll see that it's big enough to be able to take away our divisor one last time. And we have incremented once again our quotient on the right side of the L register so that we have reflected the last subtraction that we did. So our counter, we've done 18 shifts and our counter has gone to 0. So our looping terminates. We're not doing any more shifting and subtractions. We're finished after that one. But you'll say to yourself, but my remainder is bigger. Look at my remainder. My remainder is 16, which is bigger than the divisor. Well, sorry brother, we've used up all the bits and we've shifted one bit too far to the left. So we tidy up. This is called tidy up in subroutines that we write. When we write good code, we always tidy up afterwards. So by tidying up, we just perform one final right rotation of the A register. Notice the arrows have shifted on the A. Instead of going to the left, we're now going to the right. So we right shift, which puts a 0 in at the top and carries a 0 out at the bottom. And our final answer is 8 in our remainder and 15 in our quotient as expected. Thanks for watching Stephen Mendy's videos, and we'll see you soon again.